In our last lesson, we introduced the conic sections and shared some history behind them. We also discussed how one could cut a double cone with a vertically oriented plane to obtain a hyperbola and then shift that cutting plane ever so slightly to get a parabola as the conic section instead. In this lesson, I'd like to discuss the other two conic sections, the circle and the ellipse. In fact, I want to start with the ellipse because its equation looks very similar to the equation of a hyperbola. But before I get to the equation of the ellipse, let me remind you again of how one can obtain an ellipse from the conic sections point of view. In other words, the sort of geometric point of view. If you imagine that you have a cone and a cutting plane that is just a bit off from horizontal, then you can see that the cross section that would be cut from the cone would be a closed curve. In fact, it would look a bit like a stretched out circle, and that conic section is an ellipse. So how can we define an ellipse without using this language of cutting a cone? Well, there's a really good working definition that has a geometric flavor that feels a lot like the definition we saw last time with a hyperbola. Let me give you that definition of an ellipse here. Start with 2 points, which I'm going to call F1 and F2. They're the foci of the ellipse. Each one by itself is called a focus of the ellipse. Then the ellipse associated to those 2 points F1 and F2 is the set of all points in the plane such that the sum of the distances from each of the points on the ellipse to the 2 foci is a constant amount. Now, this should trigger something in your memory. In the previous lesson, we saw that definition of a hyperbola, and the definition of a hyperbola is extremely similar to the definition of an ellipse. In fact, they only differ by one word. In the definition of hyperbola, that word was difference, and now in the definition of an ellipse, that word is sum. So we need to pay attention to this sum of distances of the points from the ellipse to the foci. And that's where the geometric definition of an ellipse is really coming from. It's amazing how that one word changes the shape from this hyperbola with its 2 branches going in opposite directions to this beautiful closed curve, which is an ellipse. Now, let me share one more thought about an ellipse before we actually get to the algebra of the equations. It turns out that sketching an ellipse is actually a pretty easy thing to do. Here's how you might do it. Take a piece of flat cardboard or something like that and place 2 push pins or thumbtacks into the cardboard. Those 2 push pins are going to serve like the foci of the ellipse. Take a piece of string, tie it into a loop, and put it around the push pins. Now, take something like a pencil and use it to push the string along until it's tight. You're basically then making a triangle, if you will, but once you've pushed that pencil in, you're actually going to build a triangle now. Now, with the goal of keeping the string from getting loose, you start moving the pencil around on the cardboard, making a mark on that cardboard. And you move it around those 2 push pins as much as you can. What happens? Well, the string makes your pencil draw out this elongated, it's like a circle that's been stretched out, so to speak. That shape is not a circle, but it is an ellipse. And again, those 2 push pins are playing the role of the 2 foci. And that's pretty cool. Okay, enough playing with this geometry. I still like the geometry, it's great, but we're in an algebra course. So let's try to look at some of the algebra behind each ellipse now as we move forward with these quadratic equations. The standard form of an ellipse or I should say the standard form of the equation of an ellipse, looks like this. It's either x squared over a squared plus y squared over b squared equals 1, or x squared over b squared plus y squared over a squared equals 1, where a and b are just some non-zero real numbers. And we're going to assume throughout this conversation that the value of a is always greater than the value of b. So when we look at the equation of an ellipse, a will always be bigger than b. Now I want to point out, neither a nor b can be 0, because then you're going to be getting division by 0. Okay, now the difference between these two equations is in those denominators. In the first equation, the denominator under the x squared is larger, because that's where I put the a squared. I put it under the x squared. In the second equation, the denominator under the y squared is larger, because I put the a squared under the y squared. When you're looking at the equation of an ellipse, you want to check to make sure you can see which of the two denominators is larger. The larger of the two denominators is going to tell you something very important about the orientation of the ellipse, whether it's stretched out in the horizontal direction or whether it's stretched out in the vertical direction. Now, notice before we go on that these equations look a lot like the equations of a hyperbola. In fact, the only big difference between the two is the presence of a plus sign instead of a minus sign. That's a major key to knowing whether an equation has an ellipse as its graph or a hyperbola as its graph. So if I just hand you any quadratic equation that's got an x squared and a y squared in it, and you can see that it's in standard form, as we've been discussing, then the key you'll want to look for is whether you have a plus between the x squared and the y squared, or a minus sign between that x squared and the y squared. So you might ask, what's the difference then between having a larger denominator under the x squared term versus that larger denominator under the y squared term? I already hinted that that's going to impact the orientation of the ellipse. But now let me tell you a little bit more about what I mean with that. If the a squared is under the x squared term, and remember the a squared is the larger of the two denominators, then the ellipse will be elongated or stretched along the x-axis. But if the denominator under the y squared is the larger of the two, then that ellipse is going to be stretched out vertically along the y-axis. So the larger of the two denominators is telling you exactly the direction in which the ellipse is actually stretched. Okay, enough with all these variables and letters floating around and all this general talk about these equations. Let's jump into some specific examples. I think that's going to help us nail down these ideas when we get some numbers in there and we can really get our hands dirty with some of these graphs. So let's look, for example, at the graph of x squared over 9 plus y squared over 4 equals 1. Notice that that ellipse is elongated or stretched out along the x-axis. It's stretched in the horizontal direction. That's because the larger denominator in the equation, which is 9, is underneath the x squared term. I want you to notice a few other facts, though. There are 4 very special points on this ellipse, and actually there are 4 special points on every ellipse. In this case, you've got 3, 0 and negative 3, 0, and those come from the fact that the square root of 9 equals 3, and 9 was one of our denominators. So those 2 points are important. You also have the points 0, 2 and 0, negative 2. And those 2 points come from the fact that the square root of 4 is equal to 2, and 4 was the other denominator in the equation. These pairs of points act like endpoints of 2 very special line segments. The longer line segment is called the major axis of the ellipse, and the shorter line segment is called the minor axis of the ellipse. So we have now these 4 points and these 2 axes inside the ellipse. Also, the endpoints of the major axis of the ellipse, in this case those are 3, 0 and -3, 0, have special names. They are called the vertices of the ellipse. So there's a lot going on with any one of these ellipses, and you really want to understand this terminology because a lot of this vocabulary really comes up in a variety of math books that are dealing with conic sections. Now, let's look at the graph of another equation. This time I want to look at the equation x squared divided by 16 plus y squared divided by 25 equals 1. Now, notice that that's got an x squared in it, it's got a y squared in it, and it has a plus sign between the x squared and the y squared. That tells me that the graph of this is going to be an ellipse. And in fact, it's this very ellipse that you're seeing right now. Notice that this graph is actually stretched in the vertical direction along the y-axis. Why is that happening? Well, it's because the larger of the two denominators, in this case 25, is sitting under the y squared term. And since the larger denominator is under the y squared term, the stretching, if you will, happens along the y-axis. I want you to notice that the vertices of this ellipse are at the points 0, 5 and 0, -5. Those are both on that y-axis, and that the major axis of this ellipse is the line segment that connects those 2 points. Notice where the minor axis is located. It's now in the horizontal direction on this ellipse, and it's the line segment that connects -4, 0 to 4, 0. Notice that in both the cases we just looked at, the vertical line test was violated. In any ellipse that you draw, you can always draw a vertical line of some form that is going to cross the ellipse in more than one point. In fact, it'll cross the ellipse in either 2 points, or if you just use the vertical line right on the edge, it'll only cross 1 point. But the point here is the vertical line test is violated by every ellipse. And that means that every ellipse fails to be the graph of a function. So no matter what function you're studying, its graph can never be an ellipse. But even so, the ellipse is a very important object, and we want to be studying it as much as we can. It has a bunch of interest in its own right. Now, let's look at several more examples of equations and graphs for ellipses just to make sure we've got all the different nuances down for these equations. So here's one I want us to look at. Maybe you could try this one on your own before we look at it together. Determine the graph of the equation x squared over 49 plus y squared over 81 equals 1. Okay, let's talk through this for a moment. First, notice that this equation is already in standard form, and we're dealing with an ellipse. I've got an x squared term, I've got a y squared term. They're added together both on the left-hand side of the equation, and the right-hand side of the equation equals 1. So this is definitely the equation of an ellipse, and the equation is already in standard form. Next, what should you look at next? You should look at where the denominator is larger, and in this example, the larger denominator is under the y squared term. So this graph is going to be an ellipse which is stretched in the vertical direction along the y-axis. That means the vertices of the ellipse will be on the y-axis, and they'll be at the points 0, 9 and 0, -9. Why are those coordinates 9s? Because the denominator there was 81, and the square root of 81 is 9. And remember, 0, 9 and 0, -9 are the endpoints of the major axis of this ellipse. Where are the endpoints of the minor axis located? Well, they're going to be located at 7, 0 and -7, 0 along the x-axis. And notice that minor axis is shorter than the major axis. Why 7, 0 and -7, 0? Because the denominator under the x squared term is 49, and the square root of 49 is exactly 7. That's where those 7s come from. In fact, if you think about it for just a second, if you plotted those 4 points, the endpoints of the major axis and the endpoints of the minor axis, and just connected the dots, knowing that you're supposed to have an ellipse, you'd get the graph that you want, and you'd see that immediately. Now, before I move to the next example, we should talk about one more term that's related to an ellipse, and it's a very important one because it tells us something about the shape of the ellipse. So let me give you that piece of terminology here. It's called the eccentricity of an ellipse, and it's just defined to be the ratio of the length of the minor axis divided by the length of the major axis. So in the example we just did, the eccentricity would be 14 divided by 18, which of course is the same as 7 divided by 9. You see where the 7 and the 9 are coming from if you look at those endpoints of the minor and the major axis. Now, let's talk about this. What is the eccentricity actually measuring? What is it telling me, that 7/9? Well, the eccentricity actually refers to the flatness or the roundness of the ellipse. I want you to think for just a minute. The eccentricity can never be bigger than 1 because it's the ratio of the minor axis length divided by the major axis length. And the minor axis is always smaller than the major axis. So the eccentricity can never be bigger than 1. But when the eccentricity is close to 1, like in the case of 7/9, that's pretty close to 1, then the ellipse that's related to that is going to be relatively round. It's going to be close to a circle. It won't be a circle. It'll still have some flatness to it, some stretchedness to it. But an eccentricity close to 1 means that the ellipse is trying to be close to very round. If the eccentricity is small and closer to 0, then the ellipse is going to be very flat. It's going to be stretched out quite a bit so that its width really looks quite flat in the process. So eccentricity is trying to tell me something about the flatness or the roundness of an ellipse. All right, let's look at another example now with this in mind. I think you should try this one yourself, but remember, first you need to make sure that the equation is in standard form before you can actually graph such an ellipse. So here we go. The equation I want us to look at is 2x squared plus 50y squared equals 200. Let's graph that ellipse. Okay, now the first thing you've got to do before you can graph that ellipse is get that equation in standard form. The thing that tells you it's not in standard form right now is definitely that 200 that's on the right-hand side. So the way we can make that go away is by dividing both sides by 200. Now, notice that this thing is definitely going to be an ellipse even before I divide by the 200 because I have an x squared term and a y squared term on the left-hand side, and they're both being added. So I know it's an ellipse, but I don't know which ellipse it is yet because I don't have the equation in standard form. Let's divide both sides of it by 200 and let's see what we get. The right-hand side is simply going to be a 1, which is what we want if we want this to be in standard form. The left-hand side, after we simplify both of the fractions, is going to be x squared divided by 100 plus y squared divided by 4. So my equation is going to be x squared over 100 plus y squared over 4 equals 1. Now, once you have that equation in standard form, you should ask yourself, where is this ellipse going to be located? Or actually, put more directly, is it going to be stretched in the x direction or is it going to be stretched in the y direction? Well, which term has the larger denominator? In this case, the x squared has the larger of the two denominators, and so the ellipse is going to be stretched in the horizontal direction or along the x-axis since it's the x squared term which has the larger denominator. You also can tell them where the vertices are. They're going to be at negative 10, 0 and at 10, 0. Where are those 10s coming from? Square root of 100. That's right. 100 is that denominator. Square root of it is 10. So the endpoints of the major axis are at negative 10, 0 and 10, 0. Where are the endpoints of the minor axis? Well, they're going to be on the y-axis then. And what are their locations? Well, they're going to be at 0, 2 and 0, negative 2. Where are the 2's coming from? Square root of 4. The denominator under the y squared is a 4. So your ellipse now can be drawn quickly, and it's going to look like this. Plot those 4 endpoints and just draw the ellipse in. Now I want you to notice something. That ellipse, once you've drawn it, is actually pretty flat. It doesn't look round. It doesn't look like it's trying to be a circle so much. Why is it flat? Well, let's look at that eccentricity that we talked about a moment ago. Notice that the eccentricity here is going to be length of minor axis divided by length of major axis. That's going to be 4 divided by 20, or 2 divided by 10, if you want to use the 2 and the 10, which are coming out of those endpoints of the axes. And 2 divided by 10 is 1/5, which is 0.2. That number, 0.2, is closer to 0 than to 1. And that immediately tells me that the ellipse here has to be pretty flat, because the eccentricity is closer to 0 than to 1. Okay, we've talked quite a bit today about ellipses. I'd like to turn our attention just a moment to the last type of conic section that is part of the 4 conic sections, and that's the circle. So let's change directions just a bit now, away from ellipses, and talk about circles. First of all, how is the circle created as a conic section? Let's just make sure we remind ourselves of this. If you take the cone that Apollonius would have started with, and you cut it with a truly horizontal plane, so the plane needs to be purely horizontal, the cross section that you would see is a circle. Honestly, for me anyway, of the 4 conic sections, that's the one that makes the best sense, okay? But there's actually another cool way to think about the circle given all the things we've already talked about with an ellipse. Now, it's going to sound kind of theoretical, but just stay with me for just a second. Picture in your mind an ellipse. Remember, when I talked about drawing the ellipse on a piece of cardboard, there were 2 push pins that were holding the original string. Those 2 points are the foci of the ellipse. Now, I want you to imagine that you could lift those foci and actually move them toward one another. Now, what does that do to the ellipse? Well, one thing that it does is that it makes the ellipse less flat and more round. The foci of a flat ellipse are actually quite a ways away from one another. As you start to move those 2 foci towards one another, the ellipse becomes more round. So you end up with those foci closer and the ellipse trying to act more like a circle. In fact, if in theory you could move the 2 foci so that they're one on top of the other, basically so that there's only one focus, then the ellipse would actually become a perfect circle. So in some sense, a circle is really just a special kind of ellipse if you really only allowed yourself one focus point. I think that's pretty cool. It's pretty theoretical, but it's pretty cool nonetheless. Now, enough of that theory. Let's get right to the equations for a circle. Well, there's really only one equation for a circle. There aren't 2. And the standard form of the equation of a circle, which is centered at the origin in the xy plane, is given by x squared plus y squared equals r squared, where r is the radius of the circle. So, in fact, the conic section definition of a circle is that it's the set of all points which are a specific distance from the special point that we normally call the center of the circle. And the given distance, that special distance, is the radius of the circle. Now, you might still not believe me that these circles are cousins of or relatives of ellipses. So let me try to convince you in one more way. Take the equation x squared plus y squared equals 36. Now, given what I just told you about equations of circles, that is the equation of a circle centered at the origin, and the radius is 6. One error that some students make is that they might tell me the radius is 36. Remember, the radius is always the square root of that number on the right-hand side. Now, that's a circle of radius 6. What if I were to divide both sides of that equation by 36? Then I would end up with x squared over 36 plus y squared over 36 equals 1. Now, if you look at that the right way, it looks a lot like the standard form of the equation of an ellipse. But what's the difference? Well, the difference is that the two denominators of this equation are the same. They're not different. And that's what sets the circles apart. When those two denominators are the same for both the x squared and the y squared, and there's a sum in between, when those two denominators are the same, you know you don't have an ellipse, you actually have a circle. So these guys are really closely related. Their equations can be made to look very, very similar, but they have a slight difference between that circle and the ellipse. Now, let's do a few examples as we finish this lesson, just to make sure we've got this circle stuff down. First, try this one on your own. Sketch the graph of the circle x squared plus y squared equals 49. Okay, the graph of this equation is a circle. It's got an x squared, it's got a y squared, they're being added. It's a circle centered at 0, 0, and the radius is 7 because the square root of 49 is 7. Remember, the radius is not 49, the radius is the square root of 49. So this means that points like 7, 0, and negative 7, 0, and even 0, 7, and 0, negative 7 are all on the circle. If you just plot those 4 points and just connect them in a nice way, you're actually going to get the circle that you want. Okay, let's look at another example pretty quickly. Sketch the graph of the equation 4x squared equals 36 minus 4y squared. Now, that's actually a pretty tricky equation, and there's a reason it's tricky, because you look at that minus sign and you might say to yourself, this must be a hyperbola. But the problem is that the equation is not in any sort of standard form. Did you notice that all the standard forms had the x's and the y's all on the same side together? This equation that I've started you with doesn't have all the x squareds and the y squareds on the same side. So before you can decide whether you're dealing with a hyperbola or an ellipse or a circle here, you've got to move all of the x squareds and the y squareds to the same side. And I'm going to suggest we move them to the left side in this case. When you move the x squareds and the y squareds to the left-hand side, you get 4x squared plus 4y squared equals 36. And now you see a sum, not a difference. And that's important because it tells us something about the graph. Now, let's finish this just briefly by dividing both sides by 4. And when you do that, you'll have x squared plus y squared equals 9. And now we've uncovered from this new version of the equation that the graph must be a circle. It's definitely not a hyperbola because I don't have a minus sign. And it's definitely not going to be an ellipse because the coefficient of the x squared and the coefficient of the y squared are going to be the same. They are the same. And therefore, the graph of this is a circle. It's centered at 0, 0, and its radius is 3. So you can draw that pretty quickly. Now, if you've been following along, you should have a pretty good idea by now of whether a conic section's equation corresponds to a parabola, a hyperbola, an ellipse, or a circle, just by looking at the equation itself. So as we close this lesson, I'd like to actually have you quiz yourself and see how you do by matching some equations with their corresponding graphs. So let me give you those equations and then give you a moment to match those. Here we go. The first equation is x squared over 16 minus y squared over 9 equals 1. Next, x squared over 9 plus y squared over 9 equals 1. Then y equals x squared plus 4x plus 3. And lastly, x squared over 16 plus y squared over 9 equals 1. Now, let's talk through which of these correspond to the graphs. The first one, x squared over 16 minus y squared over 9 equals 1, is in standard form. The x's and y's are together on the left-hand side. Both x and y are squared, so that tells me I'm not dealing with a parabola. And there's a minus sign between the two. Which graph is that? That's got to be the graph of the hyperbola. So excellent if you found that, and that checks that one off. Next, x squared over 9 plus y squared over 9 equals 1. Okay, I've got an x squared and I've got a y squared, and they're added together. That means I'm either dealing with a circle or with an ellipse. And notice that both the denominators are equal to each other. They're both 9. What does that tell you? That tells you you're dealing with a circle. So you should have matched that equation to the circle. Next, y equals x squared plus 4x plus 3. Now notice something here. You've got some x squareds and some x's. That's fine. You only have one y raised to the first power. There are no y squareds in this equation. That immediately tells you which type of graph you have. You must have a parabola. So that third equation must be matched to a parabola. And lastly, x squared over 16 plus y squared over 9 equals 1. X squareds and y squareds together on one side, they're being added together. It's got to be a circle or an ellipse. And since the denominators are different, 16 and 9, you know that this must be an ellipse. And if you got those right, it's fabulous. If not, you might want to review the graphing we've done in the last 2 lessons just to make sure you're on track before we move on. Well, we could do lots more of examples at this point with circles and with ellipses. We could move the center, for example, of a lot of these. But for now, I think we've done enough. So I think we'll close here. Today, we've finished the discussion of conic sections by talking about ellipses and circles. Next time, we're going to shift gears pretty dramatically and move to a totally new topic, talking about polynomials of degree greater than 2.